according to the Nyquist criteria, we have arrived in the frequency response of open loop transfer function. So this is the frequency response of open loop transfer function when the omega is varied from minus infinity to plus infinity. So you get the open loop transfer function, open loop frequency response of the open loop transfer function, and we know from this GSH's number of poles at right hand side of a plane, that is equal to, you see, p equal to 0 in this case, because there is no pole at the right hand side of the S-plane. Right now, what else you have to get? Number of zeros of 1 plus GSHS at right hand side equal to what? So that is to be obtained from this polar plot or frequency response analysis and number of right hand side open loop poles. So as the number of poles at the right hand side of the S-plane corresponding to 1 plus GSHS is same as that of the number of right hand side pole of the S-plane of the transfer function GSHS. So you can get it from here, and you get the G omega and H G omega corresponding to the frequency response we know. Now the Nyquist stability criteria is that if there is encirclement, if n is the encirclement of the point minus 1 plus j0, encirclement of the point minus 1 plus j0 in anti-clockwise direction, right? So where is the point minus 1 plus j0? See, minus 1 plus j0 is the point of interest. So minus 1 plus j0 means it is having the imaginary part 0. So that is nothing but minus 1 on the real axis. Minus 1 on the real axis. So just identify the minus 1 point on the real axis. Say this is your polar plot. During the polar plot, you have identified this position. This is at the right hand side of the S-plane. Definitely in this case, the minus 1 point will be somewhere here. That is at the left hand side of the S-plane. So we consider this point as minus 1 plus j0 point. Minus 1 in the real axis is the same point as this minus 1 plus j0 point. So according to the Nyquist criteria, if the total contour formed, that means the total contour formed with the help of this frequency response analysis of open loop transfer function, if this contour encloses or encircles this point or not. Here you see there is no encirclement. If there is an encirclement, what do you mean by the term encirclement? So try this graph is like this. Say for example, this is your closed loop contour and this is your minus 1 plus j0 point, and similarly we draw this is minus 1 plus j0 point and this is your contour. So see the two graphs. What is this? Here this minus 1 plus j0 is just outside this closed path, and this minus 1 plus j0 is inside this closed path. That means in this case there is an encirclement of the point minus 1 plus j0, and that is denoted by n in the Nyquist stability criteria. So now the value of n is positive. That means if there the encirclement anti-clockwise, and n is taken as negative if the encirclement in clockwise direction. See this figure starting from here, or just write like now, this is minus 1 plus j0, say this is your frequency response complete contour. Now start from any point on the real axis, start moving. This is the direction, clockwise direction, you go there and you in the same direction come to this position. So what is this? This means there is an encirclement of 1, right? There is an encirclement of 1 of the point minus 1 plus j0. That means it is just encircling this point minus 1 plus j0 once, and the direction is clockwise. So n will be taken as minus 1, right? Similarly, if the same point I consider plus minus 1 plus j0 and say there is an encirclement, and you see the direction. Start from these positions on the real axis at any point. You start moving this direction as this is directed in this graph. So this is following this path, moving to this and coming back to this position. That means a closed path is formed and one encirclement is there and the direction is anti-clockwise. So in this case the value of n will be equal to plus 1. So that is how the encirclement of the point minus 1 plus j0 is measured. Either that is encircling the point minus 1 plus j0 in clockwise direction or anti-clockwise direction, and number of encirclement is taken as plus 1 minus 1 plus 2 minus 2 plus 3 minus 3, whatever you will get from the graph itself. Coming back to the NYQUIST stability criteria. NYQUIST get n encirclement of minus 1 plus j0. Right, next you have to find out number of poles at right hand side of S plane. That is, in this case there is no pole at the right hand side, so p is equal to 0. Now NYQUIST stability criteria says that if n equal to p minus z. In the first part of this lecture we have started when what we have discussed is that the frequency response analysis of the open loop system will be known to you from the polar plot itself, and we need not to go to the analysis of the closed loop system and the open loop poles. That means the right hand side number of poles of the S plane, right hand side of the the number of poles at the right hand side of the S plane will be p, that is same as that of the number of right hand side pole in the closed loop system. So p can be obtained from the open loop system itself. So what is unknown is that z, right? This z is to be calculated by using this NYQUIST stability criteria. So if in this case the value of n is equal to, see, there is no encirclement. If this is your frequency response analysis of open loop transfer function, then minus 1 plus j0 just outside this contour, close contour. So n will be equal to 0 and p is equal to 0 in this case. So by using this NYQUIST stability criteria, what you get, the value of z is equal to p minus n, that is 0. So p is equal to, z is equal to 0. Z, what is the z? Z is the closed loop system, that is the zeros of the closed loop system, which is residing at the right hand side of the screen. That means if there is no zeros of the closed loop system at the right hand side of the S-plane, the system is stable. That means if z equal to 0, what happens? There is no such zeros of, that means no zeros. So for this problem, the value of z is equal to p minus n equal to 0. So z is equal to 0. That means the number of zeros of 1 plus GSHS at right hand side of S plane. So this is 0 in this case. So the system is stable, and this is the one and only criteria for a system to be stable in closed loop by using the open loop system frequency response by using the NYQUIST stability criteria. That means if the value of z is equal to 0, then only the system will be stable. If z is equal to plus or minus, the system will be unstable in nature, right? So this is how the polar plot associated with the NYQUIST control and the stability criteria as prescribed by the NYQUIST is sufficient to give whether any system will be stable or not. And in this case, what is the conclusion? I will draw the conclusion in such a way such that you can draw the polar plot NYQUIST stability criteria. You can just conclude whether the system will be stable or not. Let me summarize this part. What are the different steps? First, you take the transfer function GSHS is equal to say 1 plus 1 by 2s. Next step, you see whether this is a type 0 system, type 1 system, or else. This is the type 0 system. So if the transfer function is like GS is equal to, say for example, 1 by 1 plus 2s into 1 plus 4s, then also this is a type 0 system. So before going to analyze the system using the NYQUIST stability criteria, you have to identify whether the system is type 0 or other, type 1, type 2, and so on. So in this example, we will discuss the type 0 system. So this is a type 0 system. This also is a type 0 system. Now, if the type 0 system is given, you have to draw the NYQUIST contour. NYQUIST contour. So NYQUIST contour corresponding to the type 0 system is like this. This is your S plane, this is real axis, this is imaginary axis, and you move starting from this direction to B, to O, to A, to C, to D, and this is your R, and this is phi. So the equation of the NYQUIST contour will be equal to limit r tends to infinity to the power j phi corresponding to this semicircular path, and this phi varies from plus 90 degree to 0 degree to minus 90 degree, right? This is your first of all, you identify the type of the system, then draw the NYQUIST contour corresponding to this. This is the NYQUIST contour for all type 0 system, because there is no singular point associated here. Singular point means what? Singular point means say if you go through this point B to A, see this point where the value of S is equal to 0. That means this is your closed contour. Closed contour means there is no discontinuity in this path. So if you put the value of S is equal to 0 in your transfer function, that is type 0 transfer function, you see this will get you will get a finite value, right? Here also, if you put the value of S is equal to 0, you will get the finite value, and so on. The type 0, second order, third order, fourth order, fifth order, whatever be the different types of defined orders you will take, the value of GSHS at S is equal to 0 will be finite. So this is constant NYQUIST contour corresponding to the system given to you, which is type 0. Next step, what is the next step? Draw the polar plot, right? So polar plot corresponding to this system, this is your polar plot. Next, what you have to do, you have to just mirror image of the get the mirror image of the polar plot with respect to real axis. You get the closed contour. Now the last step is that you just make one analysis, like means analysis of the semicircular indent, analysis of semicircular path. That means put S is equal to limit r tends to infinity, r e to the power j phi. This phi varies from plus 90 degree to 0 degree to minus 90 degree at GSHS given to you. Here GSHS equal to 1 by 1 plus 2s. Now putting this value here, you will get 1 by 1 plus limit r tends to infinity to the power j phi. Already we have analyzed it and get the value of 0 with angle, as the angle of it is equal to minus phi. So phi varies from plus 90 degree to 0 to minus 90 degree. Minus phi will vary from minus 90 degree to 0 to plus 90 degree. That is your analysis. So GSHS. So ultimately you get 0, and in every cases of type 0 system, maybe first order, maybe second order, maybe third order, you get the GSHS will be equal to 0. Only the phase will be changed. So no matter about the phase, if you get the value of 0, so your polar NYQUIST plot will remain same. That means this is your NYQUIST plot. This is your real, this is imaginary. And last step is that you just put the minus 1 plus 0 on the real axis and see the encirclement n. N is equal to 0 here. P is the number of pole at the right hand side of the S-plane, that is 0 here, and P minus Z is equal to N. This is the NYQUIST stability criteria, so you get Z is equal to 0. And if the value of Z is not is equal to 0, then the system will be unstable, otherwise the system is stable. Fine. So that is the end of the NYQUIST analysis for the type 0 system, maybe first order, maybe second order, maybe third order. In the next class, we will discuss about the analysis of the type 1 system and how to get the stability for the type 1, type 2 system using the NYQUIST stability